Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the design and simulation of Class A audio amplifier in LTSpice. Okay, we will understand what is Class A amplifier. We will also understand the DC operating point analysis of Class A amplifier. We will understand the transient analysis of Class A amplifier. We will understand the AC analysis of Class A amplifier. We will also have a look how will you increase the gain of Class A amplifier. So friends, if you are new to this channel, you can join the channel membership by clicking on the join button, and once you click on the join button you see the different options here and you can sign in any of these options. So let us understand what is the Class A audio amplifier. Okay, so in a Class A audio amplifier you can see in this circuit a single transistor that is conducting all the time even if there is no input present. You can see here, since this is DC biased circuit. Okay, Class A amplifier has lowest distortion and it has 15 to 35% of efficiency. Okay, so now let us understand these three things today. How will you define the DC operating point for Class A amplifier, right? How will you do the DC operating point analysis? Then how will you do the transient analysis, and how will you do the AC analysis? And during these analysis, how your circuit behaves like that. Okay, so guys, you can see, let's go for DC analysis. So this is called DC analysis, right? So in the DC analysis, let's say we are going to understand the DC operating point. Okay, DC operating point, what is the voltage at VCEQ, operating point voltage between collector to emitter, that is VCEQ. Let us understand the DC analysis. So in the DC analysis, as you go and see the lower circuit here, you can see I have connected the coupling capacitor here, but for the DC analysis you have to open the coupling capacitor. So you can see here, you cannot see any capacitor connected on this circuit. Okay, and if you compare with this circuit, more or less both circuits are same, but you can see this C1 and C2 are removed from the DC analysis. Since you are doing the DC analysis and these two capacitor blocks the DC elements, so that is why I have removed the C1 and C2, those decoupling capacitor, for the DC analysis. Now what I'm gonna do is, in order to run the DC analysis, you have to go at the simulate button. Once you click on the simulate button, then you have to go on the edit simulation, CMD, that is edit simulation command. Once you click on the edit simulation command, you can see here the multiple options, and now you have to go on the DC operating point analysis. So once I click on the DC operating point analysis, you can see it shows that the syntax for DC operating point is .op. So you can see here the .op, and you can give any time. For this simulation I'm giving it 10 milliseconds, so that is okay. Now you can place DC .op 10 millisecond. Now you can directly go here and you can run the simulation. Okay, so once you run the simulation for the DC operating point analysis, what you will see here, you will see a window. Okay, now you can see the different parameters they have given here. You can see the VCC, which is 12 volt for this case. You can see the value of V2. Now what I'm gonna show you is this is VC, which is 6.35, right? The VC here is 6.35, and you can see the VE here is 0.36. if you want to calculate the VCE, that means VC minus VE, you will get the 6 volt. Okay, so what I'm gonna do is, here you can see your VCC is 12 volt, and by using this combination of these resistances here, R3 and R4, I am giving the DC operating point or DC bias point at 6 volt. Okay, if you VC minus VE, you will get 6.3, minus 6 0.3, you will get 6. So it is exactly biased. So this circuit is exactly biased at 6 volt, right? Even if you see your supply is 12 volt, so this circuit is biased the VCC by 2, that means your 12 volt by 2, that means the 6 volt. Okay, so this is the DC operating point analysis. I have designed this circuit in such a way that your DC biasing voltage is 6 volt, that is the half of the VCC voltage, the half of V2. Okay, the 12 by 2 equals to 6 volt. Now what I'm gonna do is, I'll run the transient analysis. Okay, so let me put semicolon here. Okay, I'm gonna run the transient analysis here, right for this circuit. Let me show you. So in order to run the transient analysis, let me delete this. Okay, and go add simulate, edit simulation command, transient, and 10 millisecond, that's okay. Let me place it here, right, and let me run the simulation and let me show you. Okay, now you can see here, this is your input voltage. Okay, maybe you can tile window vertically, right? This is your input voltage, and at output here you can see this is your output voltage. That means your output is the amplified input signal. Okay, amplified input signal, you can see here, that is the peak voltage is 6.4 volt, and you can see it is swinging from 6.4 volt to 6.2 volt. Okay, you can see the output here at output, and once you click, since this output has the DC components on it, so that is why I have connected this capacitance C2 to remove the DC components. Okay, so let me click on here, right? Once you click on here, you can see your output is how much it is? Let me show you, 107.4. it is somewhere around 107.4 or 107. Okay, so now your input signal is 10 millivolt. Okay, and your output signal is 107, right? Your input signal is 10 millivolt and your output signal is 107 millivolt. Your gain here is 10.7. so you can see here, guys, your gain is 10.7. okay, your gain is 10.7. you can see for this circuit your gain is 10.7, right? You can see here the output voltage, and you can see here the output voltage. You can see your gain is 10.7, and I don't see much distortion on this circuit. You can see it is purely looks like a sinusoidal signal. Now let me change the gain of this circuit. Let's see how it changes. So I'll introduce one more capacitor, that is called bypass capacitor. Okay, in parallel with the R7. So what I do is I keep this capacitance value to 100 microfarad, and let me show you the output now. Okay, so this is your input, right, and this is your output. Let me show how it is changing. Okay, so earlier your gain was how much? Earlier your gain was 10.7 if I remember correctly here, and now let me check this, the peak voltage for this. Okay, so now it's, I see here is 123. That means your gain is increased to 12.3. okay, Earlier it was 10.7, now it has been 12.3. Okay, so by playing these two values like R7 and R3, this emitter resistance and this bypass capacitor C3, you can increase the gain of this circuit, right? You can increase the gain of this circuit. So you can see this C2 blocks the DC components here, but the limitation of this C2, it forms a low pass filter, so it attenuates the frequency, attenuates the frequency at some corner frequency, which comes from 1 divided by 2 pi RC. Okay, now let me run the AC analysis and let me show you the frequency response for this Class A audio amplifier. Okay, so in order to run the frequency response or AC analysis, what you need to change on this circuitry is you need to change the V3. So right click on the V3, remove all the things here, right, from here, and what you can do is place 10 millivolt here and the phase is 0. So you have to do like this, right? You have to do like this, and now you can go at simulate, edit simulation command, AC analysis, type of sweep is decade, and start frequency, let's say 1 hertz to 1 megahertz. Okay, now you can see the frequency response for this circuit. No analysis found, there's something wrong, I don't see anything. Go edit simulation command, go in AC, type of sweep decade, start 1 mega, and then click OK, place somewhere here, and yeah, bingo. You can see something like this. Here you can see something like this. Okay, you can see at output. Okay, at some point of time here you can see your gain is more or less stable, and it is, let's say, 19 minus 10 dB. At this point your gain is stable and it is minus 10 dB, but if you see after this, you can see your gain is increasing at some, let us say at 10 kilohertz, your gain is minus 9.3, which is stable. After the 10 kilohertz, you can see here your gain is increasing. Okay, now you can see your gain is at 1 hertz, your gain is minus 80 dB. At 100 hertz, you can see your gain is 57. 1 kilohertz, you can see your gain is minus 28. Hope you have understood the complete analysis of Class A amplifier. Okay, how will you design the circuit in LTSpice? How will you do the DC operating point analysis, transient analysis, and AC analysis? Okay,